Hello friends of Rock the JVM, I'm Daniel, and in this video I'm going to talk about sorting lists and tail recursion in Scala. Now, this video is both for beginner Scala users and for more versed programmers. So if you're starting out, sorting lists will probably be one of the first problems you solve, and in this video you'll learn how to do it right. And if you're more experienced, you will probably have the chance to widen your arsenal with some tail recursion. So as recommendations, as always, I'm going to code the video live, and I'm going to recommend that you do so as well. And whenever you need to refresh your memory, just refer back to this video or to the article form on the blog with the link in the description. Alright, so without further ado, let's get back to our code. So I have here an object where I'm going to add a main method just in case we need to test anything, and I'm going to show you a couple of differences. Now, one of the most important things that you should do as a Scala programmer is to smash that like button and subscribe to the channel, because I'm going to torment you with videos and articles about Scala and Akka and Apache Spark and other things on the JVM. So go ahead and hit that for me and let's get started. Good. So I'm pretty sure you know the list sorting problem, but I'll state that anyway. So you are given a list of integers, and we need to create a method to sort it in ascending order such that we don't mutate the original list. In other words, we need to write a method that looks something like this. I'm going to call this sort list, and this takes an argument as a list of ints. And this will return a new list of int, which is the sorted version of the list that we receive as arguments. Now, there are a million sorting algorithms for a list, and for the purpose of this video, I'm going to use tail recursion and insertion sort because it's easiest to understand and to read and also to explain when you see this the first time in Scala in a purely functional form. Alright, now for insertion sort, we will consider a special operation called insert, and I'm going to define it inside, and I'm going to define it as an auxiliary method. I'm going to call it insert. And this will insert an element that is a number into an already sorted list such that the result is still sorted. So I'm going to call this number as an int, and let's call this sorted list as a list int. And the result is going to be a list int, which is the sorted list plus the number in increasing order. So for example, if I do insert with the number 2 into the list 134, abbreviated like this so that I don't write it in the proper Scala way, I should get the list 1, 2, 3, 4. All right, so we need to insert the element that we called number in the proper order, in the proper position in the sorted list without mutating it. And by the way, this problem is a common interview question for software engineers, and for imperative languages or for more common languages, this is usually easily solved, but in Scala or in a purely functional language, this problem is a little bit harder. So here's how we will approach this. So I'm going to say the following. If the sorted list is already empty, or the number is smaller than the first number in the list, then it makes sense that the number should stay at the first position of the resulting list. So I'm going to say the following. If sorted list is empty, or number is less than or equal than sorted list head, which is the first element of the list, I'm going to return the number prepended to the sorted list. So I'm going to say number, my cursor was in the wrong position, number, colon, colon, sorted list. Otherwise, that means the sorted list is not empty and number is bigger than the first element of the list, and we need to somehow insert the number inside the list. But we can think in a different way. We can think that the sorted list's head should stay at the tip that is at the first position of the resulting list. For example, if we insert 2 into the list 134, the head of this sorted list, the number 1, should still be the head of the result. And so I'm going to say sorted list.head prepended 2, so we make sure that sorted list's head stays at the first position of the result. And after that, I'm going to recursively call insert with the number and the remainder of the list, sorted list.tail. So this is how we approach this algorithm in a purely functional way. We create a new list and we call the function recursively. And let me give an example about how this should work. So if, for example, I do insert with the number 3 into the list 124, we should get at the end the list 1, 2, 3, 4. But we will follow the code and we'll say that sorted list is not empty and the number 3 is not less than sorted list's head. And so we'll get sorted list.head, the number 1, prepended to a recursive call with insert with the same number 3 and the remainder of the list, which is the list 2, 4. Now, this will be 1 prepended to, and insert of the number 3 with the list 2, 4 will again have to go through this code. And in this case, the sorted list, which is now this argument, is not empty and 3 is bigger than 2, and so we will go this route again. So we will say 1 prepended to 2, which is prepended to insert with the number 3, and the list composed just of the number 4. And at this point, this recursive call will go through the first condition here. The sorted list is empty or the number 3 is less than the number 4, which means that we will get 1 prepended to 2 prepended to, and then we have this expression over here, which is 3 prepended to the list number 4. And then at the end, we will get the list 1, 2, 3, 4. Now, given this operation, we can then sort a list by inserting the numbers in order into a sorted fashion. So here's how I'm going to think about this. So you probably know that because this is a code block, we will have a single expression which will denote the returned value of sort list. And so I'm going to say if the original list is empty or the list tail is empty, that is a list of only one element, I'm going to return that same list. So there's nothing to sort, and I'm going to return that same list. Otherwise, I'm going to call insert with the list's head and a sorted list, which is a recursive call to this big function. So I'm going to call this sort list. And I'm going to pass the remainder of the list, list.tail, and that should be it. So assuming that the sort method works correctly, then all I have to do is insert the list's head into the sorted version of the remainder of the list. And I'm going to give you a small example of how that would work. So let me create a small list. Let's say we have sort list with 4, 3, 2, 1. And if I call this method on 4, 3, 2, 1, we'll go through this expression over here. The list is not empty and doesn't contain a single element. So I'm going to say insert with the list's head with the number 4 and sort list with 3, 2, 1. Now we need to first evaluate sort list of 3, 2, 1. So we will need to say sort list of 3, 2, 1 is insert with 3 and sort list with 2, 1. All right, but then we need to evaluate sort list of 2, 1 first. So I'm going to say sort list of the list 2, 1 is insert with the number 2 and sort list with just the list constituting of 1. And first we need to evaluate sort list of 1. And sort list of 1, fortunately, finishes here because for the if-else branch, the first condition is true. The list is empty or the list tail is empty. So we will return the list 1. And so this will be insert with 2 and the list 1. And assuming that insert works correctly, and we've already proven that it does, this will be the list 1, 2. Now we'll need to go back and say sort list of 2, 1 is the list 1, 2. So this will be insert of 3 and the list 1, 2. And assuming insert works correctly, this will be 1, 2, 3. And finally, we have insert with the number 4 and the list 1, 2, 3, which is the list 1, 2, 3, 4 as expected. So this is how you can sort a list with insertion sort in just something like 5 or 6 lines of code. This is pretty sweet. And this is in a purely functional way with immutable data structures. But it has a problem because if we do, for example, print line and we call sort list and I pass a very, very large data structure, and I'm gonna pass a really big one, 1 to, let's say 100,000, and I'm going to do reverse so that we have the reversed list, so to list. So if I sort list the numbers 100,000 to 1, this will give us a slightly different surprise. And this is a crash, and it's a crash called Stack Overflow error. Stack Overflow error happens because you have too many recursive calls. So this is the peril that you face when you have a method that you want to implement recursively. So if you have large data structures, you risk crashing the stack of your application. Fortunately, we can do better, and the solution is called tail recursion. And tail recursion is a mechanism by which the recursive stack frames are reused so they don't occupy additional stack memory, causing a stack overflow. This can only happen when the recursive calls are the last expressions on their code path. So if we take a look at insert and the big sort list method, the recursive calls are not the last expressions of their code path, because look at this. Look at line 18 here. We have the recursive call in the middle of an operation here, the colon. So the computer will have to first evaluate the recursive call and then prepend an element to that. And so the recursive call is not the last expression to be evaluated. And the same thing with sort list. Look at this. Sort list is an argument to insert. And so it means that we need to evaluate sort list first before we can do insert. And this is exactly what we did in the example here in the comments. We needed to evaluate sort list first, and then we had to go back to the previous recursive call. So let's do this smarter. I'm going to define another method. Let's call this sort better. And this will be take a list as a list of ints, and we'll return a list of ints just like the previous method. And instead, I'm going to implement the insert and the sorting methods with a tail recursive technique. And I'm going to show you what that tail recursive technique is all about. Tail recursion will usually involve increasing the number of arguments in your method. So for example, if you have a single recursive call in an expression, you would use that as a third argument. Let me show you how. So I'm going to define a method called, let's call this insert tailrec. And I'm going to pass the number as an int, the sorted list as a list of int, and I'm going to store an additional third argument here that we usually call accumulator as a list int. And finally, we return a list int as a result. Now, this accumulator will have a special meaning, which in this case means all the numbers that are smaller than the argument here. So accumulator will store all the numbers in the sorted list which are smaller than the number which I want to add. So I'm going to write as follows. I'm going to say if the sorted list is empty, or element or the number is smaller than or equal to sorted list.head, I need to return a result because earlier we had number colon with a sorted list. But in this case, we have number colon sorted list plus all the numbers in the accumulator that might have been added in the previous recursive calls. And so we need to add those at the beginning of the result. And I'm going to say accumulator.reverse, and I'm going to explain why I use the reverse method here. So I'm going to say accumulator.reverse, which is a list, and then I need to concatenate that with this expression, number colon sorted list. So basically what this means is all the numbers smaller than the number that I want to add, then the number, then the remainder of the list in increasing order. So this expression will be a sorted list. Otherwise, I'm going to call insert tailrec with the same number, the sorted list.tail. That is because the head of the sorted list is smaller than number, so I need to take it out and put it into the accumulator, and then say sorted list head prepended to the accumulator. So I take the head out of the sorted list and put it into the accumulator in a recursive call. So this code is a bit harder to digest, especially when you're starting out with Scala, and that is normal. So let's work through an example. Let's say we have insert tailrec with the number 4 and then the list 1, 2, 3, 5. So you know where this is supposed to go, and the accumulator is empty at the beginning. So the expected list is 1, 2, 3, 4, 5. Now, looking at the code, that means we call insert tailrec because the sorted list is not empty and the number 4 is bigger than 1. So we get insert tailrec with the same number 4, sorted list.tail, which is now the list 2, 3, 5, and the number 1, which was smaller than 4, gets inside the accumulator. So look at what we're doing here. We're taking an element out and we're passing it into the accumulator as a recursive call. And then we need to do that further. So we have number 4 and then the list 3 and 5. I think I've compiled my code accidentally. 3 and 5 with the list 2 and 1, because the number 2 stays at the first element of the accumulator because we're doing prepending here. All right. And after that, we do insert tail rec with 4 and the list composed just out of the number 5 and the list 3, 2, 1, which is now the accumulator. And now we get to the condition where it's true because the number 4 is smaller than 5. And so we do accumulator.reverse, which is 1, 2, 3. So this is why we need to reverse the accumulator here, concatenated with 4 prepended with the list 5. And so the result is 1, 2, 3, 4, 5. Now this method is tail recursive because the recursive call happens at the end. It happens as the last expression to be evaluated on its code path. So look at that. It happens on the else branch. All right. Now we're going to have a sort method, sort tail rec, in much the same fashion. We're going to add an accumulator here, and I'm going to have a list, which is a list of int, and then we have an accumulator, which is a list of int. And at the end, we return the list of int. And here's how I'm going to think about it. I'm going to say if the list is empty, then I'm going to return accumulator. That is because if there's nothing to sort, then that means all the sorted material has accumulated here. Otherwise, I'm going to do the exact same thing, sort tail rec. So I'm doing the recursive call as the last expression of the else branch. And I'm going to pass list tail. And I need to take the list head and put it into the accumulator in a sorted fashion. So I'm going to call insert tail rec. Insert tail rec with list.head and the accumulator. So I'm trying to insert list head into the accumulator. And the third argument here is going to be the empty list, which is nil. All right. So this is how we do sort tail rec. And at the very end of the code, I'm going to pass sort tail rec with the original list of the big method. So I'm going to say list and the empty accumulator nil. So this is how we do sort better with tail recursion. And if you want to make the compiler validate that your methods are tail recursive, you can add the annotation at tail rec, which you can find from Scala annotation. And if you hit import, this will add an annotation here, which will validate that your function is indeed tail recursive. So I'm going to annotate both. And if you want to prove that the original method was not tail recursive, try adding that, and you will find a compiler error here. So you'll, if you want to compile, we do recompile, we will get a compiler error saying that it is not in tail position. Cannot rewrite recursive call, it is not in tail position. So this will be a compiler validator for your recursive methods. And sure enough, if I, instead of sort list, I use sort better and have the same arguments intact, if I run this, I should get a proper result. Not only will it not crash, but I will have a list of 100,000 numbers sorted correctly. And then you can go further. You can, of course, generalize this method for any type T instead of a list of int, for which we have an ordering or some kind of comparison method or object in scope. But the goal of this video has been achieved to be able to rewrite a purely functional stack recursive method into a tail recursive method, which will handle large data structures. Now, for everyone involved, a general rule of thumb is to use as many additional accumulators here as you have recursive calls in the same expression. So for example, if I had here insert as a recursive call in a single expression here, I have insert once, and so I would add the accumulator once in the tail recursive version. So I would add a single accumulator. But if we had something like a Fibonacci number generator where we have two recursive calls, I'm pretty sure you know how to generate Fibonacci numbers. You have Fibonacci of n-1 plus Fibonacci of n-2. Those are two recursive calls, and so you would need two accumulators here as additional arguments. So that is the first rule of thumb and the first tip. And the second tip is the fact that tail recursion or tail recursive approaches are very similar to standard algorithms, only that you operate with immutable data structures. So if you have a look at the code that I've written here in the comment, you will notice that we basically use these parameters here, the parameters of the methods, as variables because we change them from every step in the recursion. Alright, so I hope this was useful. If you liked this video, go ahead and hit the like button for me and subscribe to the channel for more videos like this. I'm posting at least once a week. And follow me on Twitter and LinkedIn. I post updates on upcoming material. And also check out the written form of this video and check out the Rock the JVM website. I have tons of materials there on Scala and functional programming and Arca and Apache Spark and so much more. Until next time, I'm Daniel, signing off.